We're now going to look at some special topics in environmental economics. We're approaching the end of the cycle, and the first thing I'm going to talk about is measuring productivity and productivity growth in the presence of the environment as an input into production. This is a bit dry, and I'm going to start by doing a bunch of derivations that do not seem to lead anywhere. But in the end, in 15 minutes or so, I will tie it all together. So let's assume that we have an economy and a total output Y, and we have two inputs that make that is labor and the environment. Of course, I can introduce additional inputs into production, capital, materials, what have you, but that just complicates the notation without changing the inside. So total output Y, it depends on the production function F of labor and environment, and total effective productivity of the solar residual A. Now we're going to change all inputs by a little bit. So we add delta A to A, we add delta L to L, we add delta E to E, and then as a result GDP goes up by delta Y. Then we're going to linearize our production function in the disturbed point. F of L plus delta L and E plus delta E is approximately equal to, this is first order Taylor approximation, to the original production plus the change in L times the first partial derivative of the production function to labor plus the change in the environment times the first partial derivative of the production function to E. And this is just a general expression that is always approximately true. We substitute this thing in here. We multiply by A plus delta A. So A times F is again Y. So we bring Y to the other side of the equation. So we have delta Y here. We of course still have delta A times F LE. And then this expression just ends here. So copying this, what we have is that the change in output is approximately equal to the change in total effective productivity times the original production plus the change in labor times the first partial derivative of production to labor plus the change in environment times the first partial derivative of production to the environment. So that is our approximate growth in absolute terms. Now let's look at our approximate growth in relative terms by dividing by Y. This thing is just divided by Y, so that is easy. This expression we divide by Y, and then we multiply by E times E. So that is what is going on here, and the same for L. And if we divide this thing by Y, then we end up here because Y equals A times FLE. And so FLE drops out and we have delta A over A. So that is our first derivation. Now we're going to change things around a little bit. In equilibrium, the price of labor equals the price of the output times the first partial derivative of production to labor. This is the marginal productivity of labor. So essentially what this says, if we put in more labor, and then this is how much more stuff we get, and this is the price that we get for selling our stuff, so this is the marginal revenue, and this is the wage, so this is the marginal cost of labor. So this is an equilibrium condition. If this is true, we bring Y to the other side, PY to the other side of the equation, and we have this expression here. We have the FDL here, so we can substitute that in here. So this expression equals this expression. And what we have here is L times PL, so that ends up here. And then here we have the Y, and the Y is of course total output, but one of the definitions of gross domestic product is that it's the sum of all income. Now PL times L is the total wage income, and PE times E is the total environmental income. So Y must equal this because that is true by definition. This is just one of the ways to measure gross domestic product as the sum of all factor payments. So we have this expression here, and then we're gonna call this thing here as the cost share of labor in the economy as sub L. That's this expression. This is equal to this thing here, so we're going to substitute it into this equation. And you're still wondering, where is he going? So the relative change in technology in total factor productivity is the relative change in the economy minus the relative change in labor inputs times the cost share of labor minus the relative change in environmental inputs times the cost share of the environment. We're going to divide everything by delta t, so nothing changes, and I'm going to change notation that delta A divided by delta t, I'm going to call A dot, and then this is the proportional growth rate of productivity, and that is equal to the proportional growth rate of the environment, and no, the proportional growth rate of the economy minus the proportional growth rate of the environment times its cost share minus the proportional growth rate of labor times its cost share. And this is just standard productivity accounting. Now, the reason that I introduced the environment and the reason that we're talking about this is because the contribution of the environment to total economic output is difficult to measure, and typically it is not measured at all. The National Statistics Office are across the world are now working towards this, but they have not succeeded in doing so in a way that is generally acceptable and in a way that is routinely done. Only a few countries do this regularly. Now this immediately implies that you mismeasure your total factor productivity. So this is the production function that is true, but we don't know E. So this is really what you do. You assume that your output is a function of all the things that you can measure as input, in this case only labor. And an important thing to keep in mind here is that we measure total output and we measure total input, but we don't measure total factor productivity. It's the solo residual. We measure A by measuring Y and measuring F, and then figuring out, oh, there's something missing there, and we call that the solo residual, and we call that total factor productivity. But it is something that is indirectly measured, that follows from measurements we make elsewhere in the economy. Now, if you're just interested in levels, that you immediately see that goes wrong. Essentially, this function here is underspecified, but yeah, we just correct for that by changing our measurement of total factor productivity A. But if you mismeasure the level, we also mismeasure its growth rates, and that follows from the derivations that you see here. If you can't measure something, but it is an important input, then essentially what you do is you assume that its growth rate is equal to the growth rate of the things that you can measure. So if we make the assumption that the proportional growth rate of the environment equals the proportional growth rate of labor, then what we have is that our proportional growth rate of total factor productivity is a proportional growth rate of the economy minus the proportional growth rate of labor inputs. And that follows from the fact that SL plus SE equals 1, because these are cost shares. They together add up to 1, right? Because if SL is this thing and SE is PE times E, then SL plus SE must equal 1. So that is what we essentially measure. If it is true that the environment grows more slowly than labor, we subtract the positive constant B, then what we have that in reality A dot over A, the growth rate of total factor productivity, is the growth rate of the economy minus the growth rate of labor times its cost share minus the growth rate of the environment times its cost share. But this is just this thing substituted in here. This is again, these two add up to 1. So this expression here is the same as here. And now we have to add double negative minus and minus. We have to add the cost share of the environment times the bias in the measurement of environmental growth. And this becomes positive. And essentially what you then have is that your labor productivity growth, or in more generally, productivity growth rate of all your measured inputs, in this case labor only, understates total factor productivity growth. Essentially, your technology progresses faster than you think because you ignore one of the inputs into your production process, and that ignored input is a sluggish one. It does not grow very fast. And if those two conditions are met, then actually you have to you're growing less fast than you think you are, because you're compensating for this sluggish input that you're missing. Now, how serious is this? Here is an example, a somewhat older example for the USA, and this is work done by Robert Repetto. He's seen when he was much younger than he is now. For the USA, this is for electricity, this is for agriculture. And for agriculture, what you see is indeed that the sort of theoretical derivation is there. If you omit the environment, as people tend to do, then you seem to grow less fast than you really do. And that is because the environment doesn't expand that rapidly, but the effect is not that big. But if instead you focus on electricity, then with the environmental inputs omitted, you seem to have shrunk. You've gone from 100 to around 90 in a 20-year period. Whereas if you include the environment, you in fact grow from 100 to 110. So practically these things can matter, and they really can mess up your growth accounting of the economy.